Remember that the frequency-severity model, or frequency-impact model, the process requires a fusion or integration of these two elements. This means breaking down a risk into its frequency, how often it occurs per unit of time, per month, per year, and its impact or severity, the monetary impact of each event. Once these items have been atomized, they must be integrated again. Here, a common mistake inherited from the qualitative risk domain often occurs: simply multiplying frequency by severity. Multiplying frequency and severity is correct only when applied to the mean. However, it does not yield accurate values at the extremes of the resulting distribution. This can lead to overestimating the size of the tails, resulting in undesirable consequences, such as incorrectly calculating probabilistic contingencies. For example, if a probabilistic contingency is set at the 80th or 90th percentile and it is miscalculated, excessive contingency values might be assumed. So there's three approaches to integrating frequency and impact. We will proceed to integrate frequency and impact using these three different approaches. Remember that for frequency we define a Poisson distribution with an average, a lambda, of 4. The probabilistic graph of this distribution shows that the most frequent events are either 3 or 4. For example, the probability of 8 events occurring is approximately 3 to 4%. For 9 or 10 events, the probability decreases progressively to nearly 0. On the impact or severity side, we use a log-normal distribution which requires two parameters, a mean of 100 and a standard deviation of 150. This creates a highly asymmetric distribution, where the mean is surpassed by the standard deviation, resulting in a strong concentration of low values with a long tail extending to higher values. So the first approach is direct multiplication. We multiply the cell containing frequency by the cell containing impact. This approach is simple but problematic, as it exaggerates the tails, especially when frequency and impact simultaneously generate high values on certain iterations. A second approach is a one-to-one generation. For this approach, we use the Poisson distribution to generate the number of events, the frequency, and for each generated event, we independently assign a monetary impact using the log-normal distribution. For example, if 8 events are generated, each will have a different random impact according to the log-normal distribution. If no event occurs, the impact is 0. Afterwards, all the generated impacts are summed for each iteration. This approach accurately captures variability in the tails. Now we compare the two approaches. We run 10,000 iterations and compare the resulting curves. The mean. On both curves, the multiplicative and the one-to-one, they tend to be similar in terms of the mean. On the 95th percentile, the differences emerge here, with the multiplicative approach showing more exaggerated tails. And at a maximum, at this point, the multiplicative method can generate values up to double those produced by the one-to-one approach. This demonstrates that the multiplicative approach, by assuming events with high frequency and simultaneously high magnitudes, exaggerate values in the tails. There's a third approach, which is a convolution with specific functions. To avoid errors, we use a convolution function. This function automatically generates frequency using the Poisson distribution with lambda equals 4 and integrates the impact values using the log-normal distribution with a mean of 100 and a standard deviation of 150. In tools such as Easy Risk Quantum for Excel, this convolution function is built in and automates the whole process. So we view the results of this convoluted approach. After running the simulation with this third approach and comparing it with the other previous two, the mean matches the previous approaches. The 95th percentile shows significant differences from the multiplicative approach, aligning more closely with the one-to-one method. The maximum. The convolution approach avoids exaggerating the tails, delivering more realistic results. We conclude. The correct approach to integrate frequency and impact is through proper convolution, which respects the probability nature of both components. While direct multiplication is simple, it exaggerates the tails and produces unrealistic results. In advanced tools such as Easy Risk Quantum for Excel or the platform cloud-based application, this convolution function is readily available, allowing for efficient and precise integration using a Poisson distribution for frequency and a log-normal distribution for impact.